first goal was to live longer than my father, who passed away at 55.
Oh gosh, well mine died at 48, and I had a
Well, I hope you can swim outside the swimming pool.
Yes, nice. Oh, I've already.
Interesting.
Ted, how are you? Yes. I'm trying to get him. Well, in fact, I'm going to. Well, we're both working. So I'm about to get all of the reanalysis cloud cover data, 500 millibar temperature data, and precipitation data for all the tropical glaciers. Yes, thanks, Ted.
We're pretty close. I know. First started. I know. Anyway. Well, why don't we get started? I don't know if you got the camera on. Oh, there, okay. It's pointing to Jim, it's pointing to me. It is with great pleasure that I introduce our speaker today, Dr. Compton Tucker, Jim Tucker, whatever. Tuckaroo, I think the emails.
Yeah, that's the latest. There are many variants on my name, but let's stop there.
Call what you want. And our first post-COVID distinguished lecture, so yet still many are online as opposed to being physically in the room. So, but thank you for joining us. So Jim is a native of Carlsbad, New Mexico.
Yes, God forgive me. I hope she does.
And I don't know, can they hear me? Okay, good. Received a BS degree in biological sciences. Well, you wrote the year, so I'm going to say it. In 1969, okay. From Colorado State University in Fort Collins. MS in 1978, PhD in 73, and PhD in 75. That didn't make sense the way I was reading it. Both from Colorado State and the College of Forestry. He did what I did a few years earlier. He went to Goddard as a postdoc, became a civil servant, and stuck around for quite some time. And at Goddard, Jim used satellite data to study the Earth in research areas that include, I had to go through the writing, famine early warning, deforestation, desert boundary determination, ecologically coupled diseases, terrestrial primary production, food security, and identifying degraded land. So if it had to do with growth, Jim did it, and he used satellites to do it. I wasn't going to say this, but I found this fascinating. It was a part from 2002 to 2012, part of NASA's space archaeology program. So working with different satellite data sets. And
No, it was all ground-based.
Oh, sorry, with remote sensing techniques, with ground penetrating, radar, magnetometers, with archaeologists to map ancient sites. I should let you tell. You should introduce yourself, Jim.
You're doing great, Walter.
The obligatory 220 journal articles, all of them fabulous. I won't go through the citations.
There are one or two that embarrass.
A tremendous record, though, of publications.
H index of 130.
Yeah, that we have or had a colleague who used to get really angry when we brought up H indices, so I'm leaving that out. Yeah, respect for that colleague. Adjunct professor, University of Maryland, consulting scholar at Pennsylvania's Museum of Archaeology and Anthropology. I love this, his words. Taught introduction to remote sensing 7 times at University of Maryland, which forced me to learn the subject better. That's true. Teach it, learn it. Number of radio and television appearances, fellow of the HEU and AAAS. Several particularly notable awards, including National's Exceptional Scientific Achievement Medal, the Pecora Award, didn't say Nashville, NASA's, Pecora Award from NASA and the USGS, National Air and Space Museum Trophy for Current Achievement, and then awards from all over the country, from Sweden, Denmark, Mongolia, and I found this interesting. I'm sorry, all over the world. Sweden, Denmark, Mongolia, and Missouri. That was pretty impressive. But there was one Jim is particularly proud of that I'm going to let him speak to, which is his Senior Executive Service Meritorious Achievement Award in 2017. So with that, I'll let you introduce or explain that award, and I know that was a long intro, but there's a lot to say about Jim, so please join me in welcoming.
The party girl and flunked out for that reason. Now, no, well, she's older than I am, so I didn't make that connection. Now, Waleed mentioned that I won in 2017 from President Trump a Meritorious Service Award. So I was nominated for it after he was elected, and I get a phone call from a Trump appointee at NASA headquarters who said, Dr. Tucker, you've been nominated for this award. There's one big problem, and there's something that's really good about it. So I said, what's the problem? And they said, climate is mentioned too many times. And so I said, well, what can we do about it? She said, well, I'll change it to weather. And I said, that's fine, weather through time is climate. And then I said, well, what's the good thing? And she said, all of your degrees are from state universities. And that's good because we don't like people from the Ivy League or the University of Michigan, MIT, Caltech, etc. And I said, well, I had no idea about the pecking order of universities. I just wanted to go to Colorado so I could ski. Anyway, so I got the award and then paid the tax and donated the balance of it to good causes, which I won't go into. Okay, so more recently I've been working with commercial satellite data from Maxar, which we get in NASA for free. You just have to figure out how to store it. At the moment, we can't add any more disk storage for Maxar data because there is a limit of 2 kilowatts of power to our supercomputer center, and they can't add any more disk storage. So we're sending it all to Amazon Web Services, and then they'll charge us when we retrieve it. So using commercial satellite data, a gaggle of my coworkers and I have used a large volume of Maxar data to map individual trees using machine learning, a massive amount of high performance computing, and then subsequent analysis from this area from the Atlantic Ocean to the Red Sea, on the south side of the Sahara and north of the Equator. And these are all my co-authors. Several of them we would have dropped from the paper. But if you do that with Nature and Science when a paper is in review, this triggers an automatic re-review usually because the editors think someone disagreed with the paper. So here are all the authors in the paper. So this is just a summary again. We used 1/3 commercial Maxar images. We got them for free. If we would have paid for them at $1 or $10 an image, you can see, or $20 or $30 or $100 per image, they go for much more than that, it would have been a phenomenally expensive undertaking. We studied in areas as large as the United States and Alaska combined. With our machine learning, the learning part was 89,000 training data of individual trees. The second author on our paper, Martin Brandt, did that for our proof of concept paper, which was published 2.5 years ago. He had to take a 3 or 4 month vacation after that because he was literally burned out. We used a large mass of core hours on the NSF supercomputer Blue Waters, about 60 million core hours. And we had to process an array that was 2 times 10 to the 13th elements. We mapped a large number of individual trees, 10 million trees in the semi-arid area, and I'll show you how we define a tree in a second. And when we converted all of our tree crown data into tree carbon data, it totaled 0.84 petagrams of carbon in leaf, wood, and roots at the individual tree level. And we have a view, and that put us in a box. How do you get out of this? How can anyone use this massive data? Well, we had to develop a viewer from tree 1 to tree 10 billion at the 50 centimeter scale, and I'll show an example of that. So it's a pleasure to be here again. So this is what it looks like, the same location, you see the same tree, and this is in Senegal at about 15.5 degrees north latitude. There's a marked rainy season and a marked dry season. So we use the dry season when trees remain green with their green crowns. So that's shown here. This is an NDVI profile from our GLAM site where you can access MODIS NDVI data for any location. For this cell, this is the profile. So this is 15.6 degrees north. Now this is our definition of a tree. It has to have a green leaf crown and it has to have an associated shadow in conjunction with it. So here are the individual pixels of this tree, which is right here, and the crown area of this is 30 square meters, and this is the associated shadow, and this is the tree here in the PAN band and in the NDVI band. So this is our definition of a tree. This is an example showing for this particular tree, which we map. It's this tree here. We don't map all of this other stuff because it's not green, or if it's green, it doesn't cast a shadow. In our study, we mapped 9.9 billion trees. Gosh, this is sort of taking off on its own. In this area from down to this line right here. In the whole area, we actually mapped 13.5 billion trees, and we also mapped 1.5 billion bushes, but they're excluded from this. This is a picture of me in 1981 when I was working in this area, right here. Time flies when you're having fun, and as Pierce Sellers said, it's fun to work with your friends, and that's the only way to work. So now for some reason, this sort of has a hair trigger. So these are some of the results from our study. The paper was published in Nature. You can access it, and you can get it online and get all of the extended data. So for all of our 0.84 petabytes of data, here we have the carbon density per hectare versus rainfall, and here is the carbon density per tree in megagrams of carbon. You multiply that by 1,000 and you get the kilograms of carbon. So we work at the individual tree level, so we can have data like this at, again, the 50 centimeter level. This is just a plot showing, this is the carbon probability distribution function over here. And here is the cumulative distribution of tree crowns. And 50% of our trees had a crown area of less than 15 square meters. So that is a diameter of about 4 square meters, right? You take 15, you divide by pi, you get 5, no. And so then it's about 2, so it's actually 4 square meters or less. And then this goes on up like this. So 50% of our data were for these smaller trees. And then here we come on up, and we have very few trees which are larger than this point. Our allometry, which we use, stops at this point, and so we have a few number of trees beyond that. So this is how our data compare to everyone else who use coarse resolution satellite data. Our data are in this envelope of gray here, and the average of that is in black. And you see that 1 is much lower, but 4 of these other satellite data sets are much higher, and Niall Hannon in purple agrees with us for part of the way, and then this diverges above 700 millimeters per year. This just shows you the amount of carbon. So we are on the low side. Our uncertainty is plus or minus 20%. This is a plot. Anytime you have a huge, humongous data set like we do of 10 billion, this is how you plot things. You have a cluster of points from the other source of information, probably 30-meter data. So you have to aggregate your data accordingly. And this is how things look. So we basically don't agree with anyone. The green area right here, which is on the lower side, and Niall Hannon agrees with part of us. So you make comparisons like this, and you end up saying, well, we need to do better, but at least we resolve things at the tree level. Now we compare the data to modeling, and these are all of the trendy models right here. Here are the trendy models, and the mean of them plus 1 standard deviation is this gray zone. Our data are on the low side of the gray zone. And so again, we do not agree with the trendy models, and so numerical simulation models of carbon in the semi-arid area are probably as good as guesses because they can't resolve the tree density, which we can. So this is our output data. These are individual tree crowns, which we map very accurately. This is the carbon in trees. Then we aggregate the carbon in trees to the hectare scale. And here's everything combined. Now the data we used, we started off with 326,000 images. They covered a total of 90 million square kilometers. We had a study area of only 9.6 million square kilometers. So we down selected from the top panel down here in terms of month. We're in the early dry season, and you see the number of years. We've since added another almost 500,000 satellite images. So let me go back here. So now let's look at some of the problems. So for some of our imagery, we have clouds, and other portions of it, we have aerosols. And the aerosols are overwhelmingly from dust storms. So this is our study area in a very obscure, compromised area from viewing the surface, from clouds and aerosols. Now, so this is one of our authors in one of these dust storms. And I've been in several of them myself, and the aerosol optical depth here is probably 1 to 1.5, maybe even higher. And you cannot see the sun. The light is completely diffuse. So in spite, I seem to have missed, I guess not. Okay, so in spite of so in our study, aerosol optical depth affected 3.7% of our study area. This is greater than 0.6. Visually determined cloud cover, which myself and 2 of my employees took part in for every part of our study, totaled 5.3%. Just under 1% of our input data did not process. And so, nevertheless, we mapped 700 million trees in the aerosol optical depth and cloud-covered areas. And we concluded that the aerosol and cloud effects were well within our plus or minus 20% uncertainty. Now I'm really puzzled by what is happening here. So let's see if I go back here. I've really missed a lot of, oh, I know. So what I'm presenting to you is what we will show tomorrow in a Google machine learning symposium. So I'll just go through that.
If you want, the other presentation's on the desktop.
I beg your pardon?
The other presentation's also on the desktop.
Oh, well, is there anyone here who's interested in machine learning? I mean, okay, so I'll go to the other one and if anyone asks any questions, but I will not repeat anything I've done. So let's see, escape. I'll close this. Yes, so here's this one. And then let me go to this. I apologize for not checking this.
And I apologize for loading the wrong one.
Oh, gosh, this is not the mode I want to be in.
Use slideshow.
Thank you. Okay, you've already seen this. These are all the authors. You've seen that. So this is the second paper in a series. We had a proof of concept paper in October of 2020, which used 11,000 Maxar scenes, only over 1.3 million kilometers. Here's our carbon paper here. We're ready now to do it again with 800,000 Maxar images. You've seen that. Now, so this is an example from digital globe data on the left of NDVI of the tree crown, and on the right of the panchromatic data. So the important thing is to have an NDVI tree crown and associated shadow. So here is what we looked at before. We saw this slide before. So in the whole area, in this whole area from 9.5 north to 24 north, we mapped 13 billion trees that had a crown area of greater than 3 square meters. So let's see. Oh, god damn. We also mapped 1.6 billion bushes between 1 square meter of crown area and 2.75 square meters. And this is what I just showed you before, where we mapped 9.9 billion trees. And so here's our challenge. So this is the landscape on the left. This is how things look in Maxar data in the middle panel, and this is what we map with our neural net. And our neural net mapping is on the order of 95, 94%, and I'll show some things on that. So in any big data set, you can only partially sample things. Otherwise, you could employ a huge number of undergraduates and graduate students, and they would leave the field. So for 6,000 trees, one person manually determined the crown area and NDVI data and compared that to the neural net. And so they were only different. These two independent measurements, neural net and manual, differed by 2.5%. We also had an omission-commission error study of this. I took part in this with 6 or 7 other people on my team, and we investigated about 800 areas that were 250 by 256 pixels, and we looked at omission and commission by class sizes. So if you look on the left, it shows the total number of errors. We had a total number of errors was about 3,800. And then if you look in the lower panel on the far left, you see the number of trees. So half of our trees were in the lower binning of 3 to 15 square meters of crown area. And that's roughly going from 2 square meters of crown diameter to 4 square meters of crown area. And that's on the small size. Now, most of our areas had no error, or had very few errors. And several of these areas, there were several problems, prone areas, and I'll show those. Now, this is one area. I'll show some areas I evaluated. This is one area I evaluated with only 1 error, and that is the omitted tree here. This also was my 2021 Christmas card. and Hanukkah card and solstice card. So there are many benefits to this. Now, this is an area where I analyzed this, and there were a hell of a lot of errors. So this is because there are a lot of bushes in this area. So here are 3 trees where you can see the shadow is cast away from the direction of the incoming sun. Here's the shadow here and here for those 3 trees. Now in areas like, if you look up here in the yellow, these are all areas which are bushes. So the shadows are all around the trees. Here, they're even on the sunlit side. So you just go through this. It's laborious work, but I didn't want to subjugate all of my employees, many of them very new, to something arduous, which I didn't do myself.
Can I just, how did you distinguish between bushes and trees?
I beg your pardon?
How did you distinguish between the bushes and the trees?
Okay, the first thing is we define a tree as having a green tree crown and an associated shadow.
Yeah, but then where do the bushes come in?
Well, first of all, the shadow has to be cast away from the direction of the incoming sun. So for example, if you look, here's a good place to look, is right here and also right here. The shadows here are all around this tree and they're on this side. So the incoming solar flux would be like this, and it would be impossible to have a shadow there. So those are shadows cast by bushes. And then we actually zoom into this. We also go to Google Earth to zoom in, and by using, first of all, where the shadows are and which direction they are cast. That's the first thing you do, and then you double check it by looking at Google Earth. Yeah, and so this was a very messy one. So everything along here in red was correctly mapped, and also in white, and then everything in yellow was incorrectly mapped. And so there's several of them here where there's shadows all the way around this, here as well, here especially, here, so on and so forth. So it's laborious, but we document this by images for every one of the 800 images we went through to assemble our omission and commission errors. So there is a compensation of sorts between omission and commission, but we have to identify where we have misclassified tree crowns, and this is how we do it. And if you'd like, we can sign you up to help us next time we do it. Now this is an area where I thought it was going to be a mess. These dark areas are all burn scars, because in our area we have a lot of burn scars. But burn scars, in this case, it's a recent fire. Now there's one very weird trapezoidal tree here, which is clearly an error. And then there are 2 trees in A and B which were mapped, which were errors as well. And what we found was, because of the burn scars, it killed all the bushes and all of the herbaceous vegetation, which might have been green. And so all of these other areas were perfectly mapped. And you can actually see the shadows in the panchromatic data superimposed upon the burn scar, which was slightly lighter. So this turned out to being 150 trees with only 3 errors. So this was surprising. So then we had confidence in our errors associated with tree crowns. And then we use allometry to go from the crown area to the wood biomass, the root biomass, and the leaf biomass. And then the carbon content of that is 0.47. So this is what Pierre Ernaud, one of the 4 authors who worked the most on this, in the back closest to the tree, and his team, they go out in the area and they cut down trees. Now this is heroic, especially when you see how they deal with roots. And so here's a tree. It's the early dry season, or it's the rainy season. And here's a tree where they're working. Our allometry comes from all of these sites here. Now, floristically, the area from the Atlantic Ocean to the Red Sea is very similar. So then they cut down the tree. Here they dig out the roots, so on and so forth. And this is how our allometry was collected. This is why we only have 26 tree crown root samples. Now for wood, we have 600, and for leaves, we have 900. But this all involved the cutting down of trees and sampling them destructively. Our uncertainty analysis in the neural net mapping was plus or minus 3.3%, and that was the crown area mapping error and the omission-commission errors. Now they offset, but there was a 2.2% difference in them. And then we had our allometric error, which was 19.5%. This is the overriding source of our uncertainty. We put all this together, and we're plus or minus 19.8 or plus or minus 20%. Now our error assumes the independence of the allometric errors, which is not correct. So this is a conservative way of doing this, but there is covariation between wood and roots. And so we are it's more in the order, I would guess, plus or minus 18 or 17%. But that's what we have in our paper. You've already seen this. You've already seen this. You've seen all of these things. Here's a summary of all these different areas which we compared spatially from different data sets. And you'll notice they vary substantially. All this is in our Nature paper. Here is the tree crown area, the carbon in trees, the carbon per hectare, and everything superimposed. This is one area where you can see there's been a 50% increase, more than 50% increase from 2002 to 2021. Same area in Senegal. There's been a massive tree planting campaign there, and they have protected trees. So there's restoration potential in these data. You've already seen that. Again, here's the breakdown. If anyone is interested, we use GeoEye, we use QuickBird, we use WorldView 2 and WorldView 3. These are all the satellite data. We organize things by UTM zones. We had complete coverage, and these are the data which were selected from 94,000 Maxar images. You've seen that. Now here's what it looks like when one of these dust storms comes along. It rolls across the landscape, and it's noisy when it gets close, then you've seen this before, no data, aerosol optical depth at greater than 0.6, cloud cover, and then everything else, where we nevertheless map almost 700 million trees. These are all the people who worked on this. It was a big crew. We had 6 of our former interns. So if any of your students are interested in an intern fellowship at the Goddard Space Flight Center, be careful that we may hire them when they graduate. So we had sort of a Moneyball team. We had a lot of young people in our team. And like any Moneyball team, they pick up skills, and other people realize they're good. And so now we've lost several of them because places would call and say, you're interested in a job, and they would say no. And they would say, we'll double your salary, and they said yes. Anyway, but it was a lot of fun, and we had a good time, and we all ended up being good friends at the end of this. There was only a minor difference between 2 statisticians over a Monte Carlo technique versus the uncertainty technique, which we used in the paper. So we consider ourselves lucky. Now, this is how we got ourselves out of the box, and then I'll stop. We had to develop a viewer. It's based upon Mapbox, and this is where we display all of our results. Now, our results for carbon are only valid down to the 1,000 millimeter per year ISO line, which I guess is right here. And then it comes up again over here. Anyway, so that's, so of course with anything like this you have a disclaimer. Certain web browsers like Google Chrome works, Apple Safari 9 above, Microsoft Edge, so on and so forth, work in the latest version of Firefox, but you can't, it's not compatible with Internet Explorer, and other web browsers. So we're going to look at this area in Niger, and then I'll conclude. So here we have all of our data, and that's the area we're looking at. Now we're going to zoom in. So one of the things about our viewer, which makes it very easy to use, let me go back, is that if you look at the top, if you type in the same, URL into the viewer, you will go to exactly that place. So now we're zooming into this area with a zoom factor, and you see the latitude, or you see the longitude and the latitude. Now we're going to zoom into here. And so here you see there are 3 different images from 2015 and 2014 and 2016, but things match up very well. Now we're going to zoom in more. Now at this point, you're looking at the polygonal representation of an average tree carbon, and you're starting to see all of the raster trees. Now we'll go in further. Here's a blow up of it. You see just the raster trees. And now you superimpose this upon the terrain from Mapbox, and you get an idea of where these are situated. These are all situated in a drainage, or in either a large drainage or small drainages. And then you zoom in even further, and you see that for the tree in the upper right-hand corner, or left-hand corner and upper right-hand corner, you can see the total carbon, the crown area, the NDVI value, and you can also access the Maxar Quick Look image for that area. And we give full credit to Maxar. And I think I will stop there. So also in our paper, we have an explanation of the machine learning and some summary figures like this, but I think I'll stop there. I apologize for mixing 2 presentations. I'll be happy to answer any questions.
Thank you.
Oh, and then one last thing. At the bottom, tomorrow, I think at 10 o'clock, the Google Machine Learning seminar series will have 3 of us presenting our work. And this is the URL to it. I think if you type in modelingtalks.org, you will be directed there. And we'll go into all kinds of boring details for the vast majority of people about our machine learning aspects of this, convolution. Of course, I think it's very exciting, but I don't want to subject all of you to it. Anyway, so I'll stop there and go back to this slide and answer any questions.
Thank you. Questions? Paul?
So do you have a sense for how much carbon might be associated with the shrubs and that might accumulate in the soil other than roots
Why don't you
compared to
repeat
this?
that? So people
Okay, so the
understand.
question is, what is your idea of how much carbon is in shrubs?
Yeah, the shrubs that were even in the soil itself that accumulates over time. It's not root material.
Well, with respect to shrubs, yes, because our allometry actually includes crown areas down to 1 square meter. And so we could actually do that. Now, we haven't done it because the number of errors increases as the spatial resolution decreases. So that could easily be done. And we suspect someone will do it. But we'll try and do it before they do. Ted.
So there's not much leaf litter or natural mulch or fallen branches in the area. That would be more carbon, but not counted because it's not associated with NDVI.
We have no idea about the litter. So we're only dealing with live trees at this point.
I'm kind of curious, and this isn't something you really brought up, but how this works environmentally, because usually trees cluster together and the shade helps preserve moisture in the soil. I don't understand how a forest grows like this in such an arid environment.
Well, in the viewer, you can sort of see that. Some places you'll see a cluster of trees, like in here. And so in some areas, you certainly find that. Now, I could go on and show you other examples where there are a lot of clustered trees. Now this, and so here we are 17, almost 18 degrees north. So this is a pretty dry area. And this is in the Air Mountains of Niger. Further south, you would encounter that. So you can use the viewer and you can find all kinds of cool things like that, but they're principally further south. If you want to see shortly after other questions, I'll be happy to show you. Uda.
If I understood this correctly, you said in the beginning the modeled carbon flux is totally different from what you measured. Can you say in some kind of number or in percent how much the observations actually contradict the model?
Yes. Well,
So again, if you can repeat that.
the question is, I think I heard it, is that you're curious about the differences between our results and others. Well, others have used 30 meter data or 250 meter data. And you can't resolve individual trees very well at those scales. Now, even if you use planet 3 or 4 meter data, that is a crown area of 4 meters is the spatial resolution of the planet data. And so other people using even planet data, much less Landsat data or any other observing system data heretofore, will miss a large number of the smallest trees, which make up 50% of the trees. And so this is one of the reasons why there are errors. When you go up to an area where there are much larger trees, then things might agree. But we are looking at everything in toto within the semi-arid area from 0 to 1,000 millimeters per year. So we attribute that to spatial resolution limitations of previous studies. In some cases, I think they're just guesses because they're so far different.
How would you do this further south? I understand that here you sort of have an individual crown and the shadow cast, but then as you go further south, you have more trees grow together.
Yes, we're working. Okay, so this technique is limited right now to where you have discrete trees, where you can observe their shadows. We're working on disaggregating clump trees by their crown area and producing distributions of crown area for areas. And the good thing about working in those areas is then you can bring into use data from JEDI, for example, or from other means of getting elevation data. So we're working on that. It's preliminary. We have some preliminary results, but this is something which we are working on.
For those who don't know, can you say a couple words about JEDI?
Yes, JEDI is a NASA laser altimeter that the wavelength is 1040. It's twice that of ICE-2. It is a laser altimeter on the International Space Station, so it's in a non-sun synchronous orbit, but it crosses, the area it covers is about 53 north to 53 south. Just back, and it depends on, but you have a lot of data. Now the JEDI carbon uncertainty where they have closed canopy for us is plus or minus 20%. So there's information in knowing the number of crowns and the crown area or the crown distribution within a given area. And so this is a potential use of Maxar data for disaggregating individual crowns. Certainly where you have discrete crowns with associated shadows, as we have done, but also further south where you have contiguous forest crown areas.
Can you say anything about the species tree,
Yes.
because, you know, I'm just thinking in northern Ghana, we had acacia, which is very low biomass per crown area, and then you have mangoes, and, which is very different, and so.
Yes. So, okay, what we have done is we have Pierre Ernaud, and in the presentation I first presented, it had a lot on the allometry. We have the species of every one of our allometric trees, and they're all available at the Oak Ridge National DAC, including the height. So in machine learning, what you do is so we have training data which come all from West Africa, from Senegal and Mauritania. And then we thought we're going to have to add more training data as we go towards the Red Sea. And we ran everything, and we didn't have to add any more training data because the species are largely the same. So we pulled all of our species together, and we are working with planet data to distinguish individual species or groups of species. I have a PhD student working on that, and she's making progress, but only in the more humid areas. So that's one of the things which could be dramatically improved would be complementing this method with some specificity in the allometry with respect to species. Now, conversely, people can use the viewer, and you can go out and you can look at this tree. So this information there comes from the tree up there, which is a brighter, stronger green. And they could say, for this tree at this location, it's this species. So I don't want to say citizen science could really help this, because I have my doubts about citizen science. But people could assemble more information in limited areas using this. And maybe what we've done is completely wrong, but there is the possibility to investigate individual trees in specific locations and see if they still exist, because our data are from time periods over the past, largely over the past 10 or 12 years. Now we have more data, and we can refine that to maybe an earlier 7-year period and a later 7-year period. So I would say in that, anyone who wants to use these data to improve things, we have the viewer, we have all of our output data.
So just so I understand, so you just took the average of all the tree biomass and applied it to all the trees? To get the carbon content?
No, this information is from that bright green area right there. It's from that particular tree.
Average allometry.
Yeah, so.
We average the allometry, yes.
Okay.
So I'll go back to that slide, unless you want to ask a question, Ted.
Does your data archive, your viewer, or access through your viewer include the spectral information from WorldView 2 or 3? That would be a path to a training set that
To knowing what you're looking at.
Yeah.
Well, it could. Right now, it only includes. So I'll hear what the NDVI was, because we only use the NDVI in the panchromatic band. Now we also organize the same data where we use all of the multispectral bands, not all, but I mean the blue, green, red, near-infrared band, the panchromatic band. We sharpen everything to the panchromatic band as well as the NDVI. So that information is potentially available for every tree. But we have not included that in this run. I mean, this was a struggle for us to even finish, and many times I've thought, Jesus, this is never going to be finished. And then arguments broke out among the statisticians, and you can imagine in a large group. And so I followed the example of Walid and trying to smooth the waters and get people to look ahead and say, we'll do that in the next revision of the work, which we hope to do. So thank you for your patience. Do you want to see some more examples of the viewer? Okay, this is the allometry. So 600 individual samples of trees on the far left for wood, where the crown area and the wood biomass was measured. For roots, only 26, and you saw what a difficult task to dig out trees. Only 26 samples here, but crown area first, as well as the root mass. And then for leaves, 900 examples.
How are the trees chosen?
I was part of the allometric team.
Okay. Like, I'm just curious, like, were the species statistically representative of the percentages?
They were in the area.
Okay.
And we would have seen substantial errors. So what we did was, in the prediction of carbon, now with allometry, we screened those data, or they were screened by the allometry people. There was a certain range of wood to root ratios which were considered acceptable. And this comes from botanical research, and the ones which weren't were not included in the table.
In other words, something went wrong with the measurement of the allometry.
Yes. Knowing what's involved, I mean,
Did it err on the side of less roots? I mean,
now, I don't know how many were excluded. I can certainly find that out. There were at least a few.
It would seem like, yeah, digging out every last root, people might take a shortcut.
Yes.
Maybe guess.
Oh,
Guess that
I
root kind of
think I
walked
certainly would, especially if it's hot,
Yeah.
you're far away from where you're based.
That's really amazing.
Right.
So I'm an atmospheric chemist, you know? And obviously as this groundbreaking work, it got published in Nature for a reason that I'd like to fully appreciate, I guess. I mean, beyond the technical challenges that we work through in terms of counting trees and sizing them and speciating them and then making them accessible in a viewer. So in terms of the transferability and the uses of this type of data, I'd appreciate it if you could take me into your community and how this unique data that are resolving on a better spatial scale is enabling fundamentally new studies.
Yes. First of all,
For the benefit of the people out there, the question is, what does this allow?
Yes.
Where does this take us?
is this just an academic exercise, or may it be useful to other scientific fields? So one of the first things we can do for the first time in savanna systems and in semi-arid areas, which are rather expanse on the planet, is determine the carbon residence time in herbaceous vegetation or bushes versus trees. And the differences will be an order of magnitude different. Now, no one has ever been able to do that because they don't know the density of trees at this fine scale. And because of the dimensions of individual trees in semi-arid areas, you have to work below an average crown diameter on the order of 4 meters.
But how do you go from what you did to carbon residence time?
Okay, so right now, Joanna Joyner is an atmospheric scientist at the Goddard Space Flight Center who's made some really recent and good work calculating gross primary production. She started with chlorophyll fluorescence. Now she's figured out some ways to incorporate that with MODIS data. So Joanna and I are about to start in an area where she has her data, and we can come in and have a representation. Now these are going to be using the MODIS climate modeling grid, 5-kilometer grid cell size data, and we'll aggregate our total tree crown area to the same scale, because we have that for any spatial resolution, and then we'll make a first attempt at the carbon residence time in a savanna system.
Carbon residence time in the terrestrial ecosystem.
Yes. But start in a semi-arid area where Joanna Joyner has good GPP data and where we have good tree crown data. And who knows how it'll turn out. It may be useful or it may not. But that's one of the things we'll do. Secondly, this will be useful to people for restoration work. So for example, the World Bank has a big program called the Great Green Wall on the south side of the Sahara. But nobody really knows if trees, which they promote to be planted, if people actually plant them. Now, in a few small areas, you can use commercial satellite data and tell that. But now we can do it for the whole zone, especially now that we have 800,000 images over this time period, so we can do it for the past 6 or 7 years, as well as an earlier time. So this will be a way to see if the restoration has actually occurred, where it's been successful, where it hasn't, and has it made a difference. And then it will increase the contributions to the Great Green Wall. So I was talking to them last week, well, why don't you support us? And of course, you always plead poverty. Oh, you know, we're having a rough time. Anyway, so they said, well, we will propose this to our next meeting in November, and we can let you know by December. So this is one ecological restoration potential, which I hope they take advantage of. And then they said, why don't you start work in Southern Africa too? And so I said, well, we're limited by electricity, as I explained earlier. Anyway.
I hope when you approach them, you refer to them by the correct name.
Well, yes.
Yeah. So we got time for one more question.
I mean, you probably have quite an impact on things that are just modeled as processes, in like the community Earth system models, where you have energy balance transfer from the Earth to the atmosphere, like the sheer count of the reflecting area of all these trees might matter, because they are not brown but green and so forth, right? So you have all these thousands and thousands of signatures of different reflectances and so forth. I mean, the modeling community is dying to have actual large-scale data. So I bet there's quite a few applications out there. And the last question was, how tall was that dust storm?
How tall is the dust storm?
How tall is the dust storm?
Out
Like
there?
500,000 meters tall, or how tall is it?
So the things we're doing right now, which may be of interest to our cryospheric friends, is we're now looking at mapping. Now, these satellites are in polar orbits, which is good because you have a lot more data the further north you go. And so we're now looking, and apparently it's very promising to use a modification of our technique to map bush and tree encroachment into the tundra as this migrates north. And you have enough data to do this every 2 or 3 years over this 15 or 20-year time period. And so we're trying to hang on until we can get that done. Now there, the problem is slightly different. Sometimes you have a smaller NDVI signal from the bush or tree, and you have a very pronounced shadow, which, I mean, it really doesn't matter with machine learning. So that's something else which we're looking at, just to have some companion data from cryospheric areas. And I really am interested in the cryosphere, including tropical glaciers, with a person we won't name who's been very tardy in finishing a paper with me, and a few other areas. And so this is something else we're doing. So, but the key thing is, for the first time, we can map the semi-arid trees with a high degree of accuracy. We just need to have a method to convert them, because you don't have allometry everywhere, into carbon. But no problem with measuring and determining the distributions and locations of tree crowns. So the Australians are talking to us right now. But this is laborious in an organizational sense, because of all the data you have to get organized. And then you have to form it up for processing. And then so far we've been able to, people provide all the supercomputer time we need. So on Blue Waters, we ran just under 100 million core hours, about 16 million about 8 million or 7 million node hours. And the more we ran, they said, run some more. So
You got them hooked. So real quickly, you'll have problems with shadow on the tundra, but I look forward to
shadow is one of the things which is very important what we do.
I know. Well, listen, thank you so much. Please join me in thanking. We have a small reception in the atrium downstairs, so I invite you all to join us. And we'll talk informally downstairs.
And if you're curious about the machine learning aspects, there will be this, this
And he'll get that for us.
I'll actually be somewhere in Syria.
Oh, okay.
You logged in.
All right, let's check it out. Free with the Lord and experience. First job.